In this module, we will continue with the controller design, and we will look at design of torque loop, which is the fastest, and then the speed loop, and then the position loop here. So let's look at our system, and we are using DC motor drive as an example. So we are trying to design this torque loop, which is the innermost and the fastest loop here. And so let's say that torque and current, they are proportional to each other, so it doesn't matter. And so this is our reference current, and this is the actual current, which is being measured, let's say, over here. And so the difference of these two goes into this PI controller, which produces the control voltage, and that times the kPWM, that is the voltage that gets applied to the armature terminals. And from this, we must subtract E sub A, which comes from the speed. So speed times Ke is E sub A. So the difference of these two acts on the armature resistance and the inductance, which is expressed in this form. This tau sub E is just the inductance divided by the resistance of the armature. So it just expressed a little differently. So the output of this block is the current, which acting on the torque constant gives us the electromagnetic torque, and subtract that from that the load torque, and the difference between these two acting on the inertia here gives us the speed here. So we have sort of an interleaved loops, I should say, and we want to simplify it to something that we recognize. So for one thing, let's forget about this load torque here under the steady state operating point. And so what you can see here is that from this point on, this part here, we can represent it like this here. So IA times all these things taken together would give us EA, and that's what we are showing here. But IA also times KT is electromagnetic torque, which acting on inertia gives us the speed here. So we recognize that, but that is really not our concern at this point. So what we will do is we can make another assumption here, that let's say the inertia is quite large, so we can ignore this term here. And if we do that, then the block diagram that we come up with is just this over here. And here you can see that this open loop gain, which is the product of these three blocks. So you have the PI controller, this over here, then kPWM over here, and the motor is represented over here. All right. So to design this thing here, one of the procedures could be that we select the 0 of this PI to cancel the motor pole. And if that happens, then you can see that the ratio of the two gains in the proportional and integral control, they will equal to this electrical time constant tau sub E. And we can then, this open loop gain can be expressed like this, where this is given in terms of these other system parameters here. And we can choose this K sub I to achieve the desired crossover frequency to be like this here. So that gives us how to choose these parameters in the torque loop. And then we come to the design of the speed loop, and here we assume that the torque loop is ideal, the current loop is ideal. So whatever is desired is delivered over here. So the gain and the transfer function for the torque loop is really unity, and this is assuming that speed loop is perhaps an order of magnitude slower than the torque loop. And so in this case, we can then select some reasonable phase margin and come up with a similar arguments the PI controller of this speed loop here. And then we have this position loop, which is the outside loop, and here we can assume that the speed loop is again an order of magnitude slower. So the position loop is an order of magnitude slower than the speed loop. Therefore, the speed loop is really ideal. So whatever is the desired speed that we want is what we get. Then the system is very simple here. We really don't need to use an integral control, and we can come up with the desired crossover frequency and bandwidth. So there are certain other things we should be aware of here, that if we have the information already for the torque that we want, the speed that we want, and the position that we want, so those things can be fed forward, so to speak, as shown here. We also should have the limits, and these limits then produce nonlinearities. So we should be aware of that because, for example, from the power processing unit, the output voltage that we can get cannot exceed plus or minus the DC bus voltage. So that type of things, those limits we must observe. And also when we have integral control, we can have this integration wind up. So we should be aware of that, and that is discussed in this chapter here. So in summary, we have looked at the design of the torque loop, the speed loop, and the position loop.